right, so if you're in Chemistry 30 and you're in the equilibrium unit, here is a really good test you can go over. It is on Quest A+, and so here is the work involved to find those answers. There's a few tricky ones, and they are good to go over, and these are all over old diploma questions, so you can be sure to see similar questions when you're writing your own tests. So the first question here, just getting right into it, you have an equation in equilibrium, and it asks you which property would not be used to determine if the equilibrium system represents the equation above, if it's at equilibrium. Wow, that was hard for me. So when you're looking at this one, this is essentially just knowing the definition. And if you're in equilibrium, these three things would stay constant and D would not. So that first answer would be D. We wouldn't be looking at mass to know if we were in equilibrium. Question number 2 is another theory question. When you are in equilibrium, which of the following stresses will cause a change in Kc after equilibrium has been reestablished? So we can stress a system, but nothing affects Kc except temperature. So you're going to go through and find the one distractor that has temperature. The rest will not matter. So catalysts don't affect Kc, adding an inert gas does not affect Kc, and adding or removing products does not affect Kc. Now the other part is this now knowing Le Chat and showing that we understand shifting. So in this case, it's asking which stresses would shift your equilibrium towards the reactants. So we want to see what would shift to the left. So the first one is about volume. Volume and pressure are based on moles in a system of gases, which is what we have. And what I like to remember is that if you increase volume, you move to the side with more moles. So I tell my students all the time that this makes sense to me. Use what makes sense to you in terms of memorizing. So if I want to shift towards the products, to the reactants to the left, I have more moles on the left-hand side. So I would want to increase the volume. So it would be number 1. Then just going through the rest, decreasing wouldn't work. If I increase the temperature, I shift away, so that would work. So number 3. Number 4 would not. If I increase NO2, I'd shift towards products, so not that one. Decrease it, I want to shift to replace it, so that would work. Number 7, increasing N2O4. Yes, if I add this in, I'm going to shift away, and then the opposite would not be true. So 1, 3, 6, 7. Number 3 here, which of the following rows identify the equilibrium law expression and compares the amount of products and reactants represented in equilibrium. So here you want to make sure you're doing your products over reactants, and we're not going to include water because it's a pure liquid. So we would only include it if everything else was liquid. And then looking at this expression in terms of your Ka value, if your Ka value is less than 1, reactants are favored. So going through this, the only one that would line up here is A. We see that the equilibrium expression is right, and you would have less products compared to the reactants because your reactants are favored. In our next one here, which got kind of squished, but I think we can still figure it out, we have the statements about the equilibrium system, and then it's asking which ones would apply. So I think I also just need to see the equation there. So the first one, there are more moles of products represented than moles of reactants. For this one, because we are not going to be including water, we do have more moles of products than moles of reactants. So number 1 is going to be true. And then based on the Kc expression, you have more products than you do reactants. So going to 3 and 4, saying less than 50% of reactants will be converted to products, that's not true because that would mean your reactants would lie to the left, meaning we'd have more of them. So the next one is true. We're converting more than 50% of reactants because we're using it up to make those products. And then number 5, just looking at our system, this one gets a little bit confusing because right now we don't know if this is endo or exo. So when it is talking about heat being whether we're shifting left or right, we need to know if we're endo or exothermic. So we can quickly just do Hess's law short, and you'd find out through Hess's law short that the delta H of the system is negative 41.2. So now if we are heated or cooled, we can see what's happening in that way. And what we would get here was number 5. So this one I think was a little bit tricky. I definitely messed up with 3 or 4. Had to think about that to go back to replace it. And I can see why, but just taking our time and then reviewing Hess's Law short. Now with this same one, it's asking what would a catalyst do to our system, and if it would amend. And so essentially here, catalysts only speed up the time it takes to get to equilibrium. So you won't have any change. And then the other part saying another stress that would cause the same effect on the amount of products is. And this one is going to take a look at C, and it was about the volume, and it was because when we're looking at it and we're all in the same state, we have the same amount, so increasing the volume isn't going to do anything. Question number 5, asking about our equilibrium expression, remembering that the exponent becomes the coefficient, and it's always products over reactants. So we would want to see this part on the product side, and then we want our reactants over here. So the one that we are seeing to be true is 5B. Coming down to this one here, here we are balancing, so you'll need to balance your expression first. So when I balance combustion, I always start with my hydrogens. Oh wait, it's not even combustion because we're not making water. So let's start just by looking what we need. So to balance this out, we definitely do need some more oxygen on this side, and then we'll have to balance out our hydrogens with a 4. So then when you do write your expression, remembering that we have products over reactants. So the products, looking at your coefficients that you'd have, would be a 4 and a 1. And then on your reactant side, you would have a 2 and a 1. Now, in this one, if you weren't sure what to write out first, just remember that it's usually in order in terms of like alphabet, but also they'll take the combinations of this, so that it could have been 1, 4 and then 1, 2. So don't worry too much about that, just knowing that you can balance it and that you can make that connection with the expression. Which of the following can act as a Bronsted-Lowry base? To be a base, you have to be able to accept a hydrogen. You also want to be, let's just take a look at here, Bronsted-Lowry. So this is an acid, so not this. You don't want to be strong, so we'll take that one out. This we don't have, it's just an ionic compound, so it just would be D. So when we split this apart, we have HCO3 negative. That negative means that you can accept that base, or sorry, an acid. Number 4 of the numerical response. So we have our Venn diagram, and then it's asking, out of those 8 things, what belongs in section 2? So what can act as both an acid and a base? So we hopefully know water can. An acid just acts like an acid. Sodium carbonate, you would just want to go take a look at what that looks like, and it will not be one of our options. Sodium hydrogen carbonate will, sorry, I don't know why I crossed that out. That will be one of our options. So number 4, because the hydrogen carbonate ion means hydrogen to donate, be an acid, and a negative means you can act like a base to accept it. You can be diproduct. You can also be monoproduct. So it's also 5 and 6. And then just these last 2, if you accept a proton, you're only a base. And if you donate, you're only an acid. So you wouldn't be in that part of both. Coming down to number 7, what are acting like your acids? So just remembering that you can approach going in either direction. So taking a look at what's happening, we see that the hydrogen is coming over to the HCO3 negative. So your HCO3 negative is what's acting like an acid on the reactant side. And then on the product side, I think it's a little bit easier to see that acid a bit clearer. So this is going to be C, which ones are acting like an acid. Moving on to question number 8, which of the following equations represent an equilibrium system that favors the products? So here it's going to be placement. So you want to look at page 8-9 of your data booklet. And if you're favoring the products, your acid has to be higher on the table than your base. So if you go to look at all the ones that are not correct, you will see that your base is going to be higher on the table than the acid. The only one that it's not is C, where HF is higher up than NO2 negative. Question number 9. So question number 9, you can take a look. I wish I wrote this down, but I believe it was 10 and I left my data booklet upstairs. You can take a look at page 10, your indicators page, and get the Ka value, and then see where that Ka value will fit on page 8-9. Okay, so when you do take a look at that, you'll notice it's closer to the bottom. And then when we're asked which one will show what will happen if you add a few drops to nitrous acid, well, you have to have nitrous acid reacting, but this is like a buffer, so the acid is going to react with the base part of the buffer. So that's this part. So these reactions would not happen. So it's one of these, and they're the same. So it's either A or B, and then you look at the color. So it is yellow if you're favoring the hydrogen ion, and it is red if you're favoring the negative, that PR negative ion. So here, when we're taking a look at this and you look at placement based on where that Ka is going to be, your acid is higher up than your base, so the product side will be favored. If the product side is favored, you have more of the hydrogen ion, the acid part of the buffer, which means you're going to be more the acid color. So this one is going to be, that one is going to be A. Question number 10 here, which of the following ions could react with the buffer in a reaction that would favor the products? So if we're taking a look, we do have the buffer system, which would be these two. If you want the products to be favored, you're looking for your acid to be higher up than your base. So you're just looking at placement here, and you'll see that the carbonate ion is higher up than the base, and so your answer is A. Question number 11, which of the following substance is amphiproduct? So being amphiproduct means you can act as an acid and a base. So it's important that you do know that term. So the only one, so this is not either. This is just a base. This is just a base. And this one is amphiproduct because they have a hydrogen to notate and a negative to accept. So it could be both. Question number 12. We have our system. And then it's asking what can be amphiproduct. So again, you have to have a hydrogen and a negative. So these ones won't work. C or D will, because you have the hydrogen and you have the negative. And then it's saying, and a conjugate acid-base pair is. So a conjugate acid-base pair is a difference of one hydrogen. So these are conjugates and these are conjugates. So they're beside each other on page 8 and 9 of the table. So this one does not work because they're different. C is going to be our answer. Number 13, which of the following rules identify the number of conjugate acid-base pairs and the number of amphiproduct species? So conjugate pairs, we have 2 of them. And then what can act amphiproduct? Well, water is one that we recognize, and then the other is if you have a hydrogen to donate and your negative. Like what, oopsie, sorry about that. Like what we're seeing here. So this is going to be C. Okay, number 14. Number 14, what we're taking a look at here is that you have a buffer system, and then it's asking what would happen if you add a little bit of acid to your buffer system. So if you added acid, you would react, wait a minute, in order to pair it with a suitable, could add that. So we want to add our acid, and which one am I looking at here? And it's going to react with the base part of your system. So that would be with the ion present, one of these first 2. And then when you are adding to a buffer, you want to maintain its pH. So we're not adding till your pH is equal to 7. You're adding enough just to resist that change in pH, and that is going to be B. Number 15, which can be a buffer system. So just remembering that a buffer system is a weak acid, with its conjugate base. And so that is with a weak base. So cannot be A because those are strong. Again, strong. These aren't even related. And this would be because once you split into your ions, you would see your weak acid with the conjugate base. So our answer here is D. Moving on and just keep going here. Taking a look at shifting. So which of the following rules identify the direction of the shift that would affect of the pH system when a small quantity of hydrochloric acid is added? So if you're adding hydrochloric acid, right, HCl, just HCl, you're going to react with the base side, and that essentially means you're taking this out of the system. So if we're doing that, we are going to shift, wait a minute. Oh my goodness, I'm losing my mind. Just kidding. This hydrochloric acid is a strong acid, so you're adding H3O3 directly into the system. So that will shift to the left. So you're shifting towards the products, but because this is a buffer system, you should not see a change in your pH. So here we should see our answer is C. Okay, now this one, I had to think about it for a second because it's talking about a weak acid and it's saying that it's dependent on the initial concentration. So I thought it was like tricking us because 1 and 3 here are strong acids. So if it's asking about a weak acid, I'm not sure why they'd pick strong ones to test. So you're just looking at the change of the concentration of all of the same weak acid. So 2, 5, and 8. That's a 5. And that's all we had to do on that one. This one with the graph, we are titrating. So it's asking in this one that you're titrating. We want to recognize that you're not between 0 and 1. So you're titrating a weak acid. And with a weak acid, you do have a buffer system. And the buffer would be in region 2 only. You don't want to say region 4 because this is when the titration ends, right? We keep titrating to get the full curve. So this is just essentially all of the acids now used up. Well, it's actually used up here, and you just have all base remaining. So part 4 is not a buffer area. It's just a beginning before you reach your equivalence point. Okay, 18, talking about hydronium. If you're going from 2 to 4, we are getting less hydronium because you are getting to be more basic, less acidic. And we also want to remember every time you move on the pH scale, you change by your hydronium by a factor of 10. So you're moving by a factor altogether of 100, and your hydronium is decreasing by that factor. So 18 is D. This next one, we have the hydroxide concentration. We have the solution of a pH of 3.50, and we want to figure out the hydroxide concentration. So this is actually more chemistry 20. We just want to turn your pH into POH, which is 10.5. And then we can go 10 to the negative POH to get the concentration. So 10 to the negative 10.5, and you get 3.2 times 10 to the negative 11. So filling this in was just 3211. So didn't have to overthink that one. Question number 7, asking for KB, given that information about the ethanoate ion. So we can look up the Ka for this, and your Ka is 1.8 times 10 to the negative 5. And now you can just use that relationship that Ka times your Kb equals your Kw. So if you have one and want the other, just divide it by your Kw. So your Ka will equal your Kw your Kb divided by your Ka. So you'd have 1.0 times 10 to the negative 14. So you probably know that number, but if you don't, it's in your data booklet, divided by 1.8 times 10 to the negative 5. If you find you're not getting this right, just make sure that you have brackets in the denominator, and we will see that our answer is going to be 5.6 times 10 to the negative 10. So filling this in, we have 5, 6, 1, 0. So I think we're about halfway through going into question 19. We have some information about a system, and we are told the concentration of the acid, and we want the hydronium ion concentration, and then the pOH of the system. So here you want to remember the formula that your Ka equals your hydronium concentration squared divided by the concentration of your weak acid minus hydronium. Now you can also remember, if you're finding hydronium, you can ignore it in the denominator. So you can now take a look at your data booklet, find the Ka value. You have the concentration, so we can fill that in, and you want to isolate your hydronium, and don't forget that you need to square root it to get that value. So your hydronium concentration is going to be that 6.7 times 10 to the negative 5. And once you have that, then you can take the negative log of that number to get your pH, but it's asking for pOH. So once you've done that, then subtract it from 14, and we'll see our answer in this case was going to be, which one? pH was 4.7, so pOH is 9.82. Looking at question 20, you have some information about, it's essentially a natural indicator, right, that changes colors, and it's asking based on this equation that at equilibrium, the rate of the reverse reaction compared to the rate of the reverse forward reaction. So if you're in equilibrium, they're going to be equal, and the pH of the solution over time, and if you're in equilibrium, it's going to remain constant. So that was more of a theory question. Now the second part of this is for a calculation. If you want the if you have the pOH and you want hydronium ion concentration, then we are going to take a look at our value here. So we have the Kc value. So I just wanted to think about number 8. The pOH, solution of solution is measured to this. So you have pOH. So we can actually go straight into finding pH by subtracting that. And once you have the pH of the system, then you can do 10 to the negative pH. And when we do that, you'll get 7.2 times 10 to the negative 10. So that took me a second. I thought it was going to be harder than that. Looking at question 21, we have the Kb value, and we have the concentration of the base, and we want the pOH. So in this one, we can use that Kb formula equals the OH ion squared divided by the concentration of the weak base, again, minus the hydroxide concentration. So just like the other types of questions, if you're finding hydroxide, you could ignore it in the denominator. So you know the Kb value, we can plug that in. You know the weak base value, you can plug that in and isolate the OH. Don't forget to take the square root. Once you have the concentration, then you can take the negative log of that. So the negative log of the concentration is going to equal your pOH. And in this case, your answer will be B. Question 22, which of the following rows identify a Bronsted-Lowry base and a conjugate acid base pair? So looking at what we're seeing here, what's acting like a base, in this case, what we're seeing that hydrogen's coming over to be donated. So we have the CH3NH2 is acting like the base because it's accepting the hydrogen. And then your conjugate acid base pair, again, don't forget you have to be right beside each other on the table. So we're seeing in this case that will have to be the one with water. Question 23. Here we have a Kb. It's asking for the Ka, and then talking about the acid, and the conjugate acid is classified as this part here. So just going over this for one moment, if you have the Kb, finding the Ka, just talking like the other question we did, we just have to divide it by the Kw. So we'll take Kw, which we get from the data booklet, divided by the Kb value. And you'll see that the 2.3 times 10 to the negative 11 is what will come up. And then looking at what we have from there and being able to describe it. So looking at the acid, if your Ka value is pretty low, it's going to be a weak acid. And then even taking a look, you only have one hydrogen to donate, so it's monoproduct. Question 24, similar question we've already done. You're using the Kb formula. So if you have the Kb formula, you have Kb there, you have the concentration of the base, you want the concentration of the OH ion, so you can ignore the OH that would have been in the denominator, and plug in your values, isolate the OH negative, make sure you're squaring to get the answer, which in this case is B. My dog is starting to whine in the background here. He needs my attention soon. Numerical response number 9. You have the pH of a basic solution, and it's asking for the equilibrium concentration of the base. So just filling this in. Johnny, be quiet. So just filling this in, you have your Kb value. If you have the pH, but you're working with a base, you need the pOH. So we'll subtract that from 14. So you would then take that value, and then we can replace that in for OH by taking 10 to the negative and then squaring it, divided by the concentration of your weak base minus the OH. So my dog's going to keep going here. So doing all of this, in this case, you're isolating your weak base. If you do need more steps here, just let me know in a comment, and I can definitely make another video showing that. But hopefully you're comfortable with rearranging. And once you've rearranged it all, again, I think the biggest thing here is don't miss the fact that we have to change that. You'll end up with the value 1.6 times 10 to the power of 6, negative 6. So you'll fill in 166 here. All right, so question 25. I'm going to skip this one. When I set this up, this is an old ICE approximation question, and it's no longer in the curriculum. So this is one, even if you try it, don't worry, you didn't have to do it. If you do it and you do use a quadratic formula to solve for X, you will find your answer ends up being B. But again, you won't be tested a question like that. This next one, you're showing that you know how to read the graph in equilibrium, and just pulling out values and also writing out the equilibrium expression. So my equilibrium expression would be the concentration of HCl cubed times the concentration of that big long compound, that PNH yada yada. And then you're dividing by the concentration of PCl3 times the concentration of NH3 to the power 3. So you're writing the expression, and then you're just looking at the graph. So if I want HCl3 at HCl3 when we're at point P, which is got cut off here, it's 0.6, and I need to plug that in and cube it. And then your P, what do I have that? NH, that does not look like an H2, to over 3. There, looking at that one, we have this value, so times 0.2, and then you just keep going and read those values. This one would have been 0.4 times 0.3 to the power 3. Plug this all in. Now, when I first did this, I found that the value was 4, and it said I got the question wrong. So here, be careful with your sig digs, and also use this part here to help you. Why I got it wrong is for a 3-digit answer, I should have had 4.00. So something just to look out for, taking your time. Now, the next few questions we have are, not this one, this is a theory question. This one, same graph, the change in the reaction conditions represented by the time Q, so Q being here, and we are not seeing any vertical lines, so it has to be a temperature change. And then we also know from the equation that energy is on the right-hand side. So it's an exothermic. So then just seeing what's happening in here, the answer has to be C. You are decreasing the temperature because you're moving to the product side. And if you're getting more product, Kc has to increase. So I can tell we're decreasing because if you're taking a look at your HCl, it's increasing. So this is going up. Your other compound that's more complicated is going up, and the other two are going down. So that's being used up. You're shifting to the right. Now, this next one, we're starting to look at ice values, or an ice table. So going through this, we have our reaction. You'll need to set up an ice chart. Your initial concentration of CS2 is 0.31. My dog is distracting me. And the concentrate, oh wait, no, that was wrong. 0.18 and then 0.31. Unless it tells you otherwise, you can assume your products are 0. So now from here, hey Johnny, shh. It's gonna get worse. We're gonna subtract x, subtract 4x plus x plus 2x. All right, let me just sorry. Okay, you should be a bit better now, let's hope. So I'm filling this in, so I'll have 0.18 minus x, 0.31 minus 4x, and then x and 2x. But it tells me at equilibrium, my CS2 equals 0.13. So I'm going to take that 0.18 minus x and set it equal to 0.13. I can solve for x. When I do that, I'll find out that x equals 0.05. And then now it's asking, what is hydrogen going to be at equilibrium? And my hydrogen's equation is here. So I'll take this value, plug it in for x, and find out that hydrogen will be 0.11 at equilibrium. Okay, our next one, oh, did that cut off a bit? No, we're good. Our next one is not a nice question, but just, I'm sorry, it is a nice question, but finding Kc. So same idea, setting up your ice chart. You have 3 moles per liter of your C7H14. And again, unless it tells you otherwise, assume your products are 0. Then use your mole ratio, reactants are used up, products are formed. Fill in your chart by adding your columns. And then it tells you at equilibrium, your hydrogen, so this one here, equals 1.20. So now that's enough information to solve for x, and you'll find out that when you do that, what will x equal here? 0.4. And then you can solve the other ones here by plugging in x, and then you can set up your Kc expression, right? Products over reactants. And plug in those values that you would calculate now that you know x. So now that we know x, we'll know what these numbers are. So we go ahead and plug that in. You're going to have, what's our first one there? 0.4 times hydrogens is 1.20, but that's to the power 3, divided by our last one is going to be 3 minus 0.4. So we do all of that, and you'll see that your answer is, do I have that one written down? Okay, I just didn't write it down, but that is what we're doing. So let me just quickly stick that in my calculator. 1, 2, 3. There we go. Sorry about not having that one ready. Okay, so just a couple more to go through here. Question 28. Again, we have another ice question. So we're setting up the same way, going through this one, and then we want to figure out the equilibrium concentration of these two. So if I ignore that chart just to begin with and fill in what we do know, and it's those starting values of initially what we have, and then I use the equation to say for my mole ratio, so minus x minus 4x plus x plus 2x. Fill in those columns, so 2 minus x, 4 minus 4x, 2 plus x, 4 plus 2x. And then if at equilibrium, you know that this part here equals 1.25. You can say 2 minus x equals 1.25 to find x equals 0.75. Once you have 0.75, you can now replace it in for x for the questions that they're asking for, and you'll find out your concentration is 1 and then 5.5. And then this is, I believe, the last question, question number 12. This is an interesting question because there are many answers depending what you're choosing to shift. So it's saying you pick what you want, then describe the shift and say what you would see. So if I just pick that first one and say I'm using a hot plate, if I add this heat to the system, I'm going to shift to the left. So that means I'm shifting towards the products. And if I'm shifting towards the products, my color is going to be more colorless than dark blue. So it would be 167. Now this would all change if I chose ice. This would all change if I was adding in NaCl or AgNO3. So this one, it really depends on what you want to pick to figure that out. And then just to remind you, if you have not followed me before, I do have a website. Please check it out. It has every unit listed with lessons and homework and practice tests. And if you did find this helpful and you made it this far, please, please, please subscribe. As always, thank you for watching.